Yes, sir.
So the one-dimensional Schrodinger equation will be IH cross del psi, which is a function of x comma t, x and t, del psi by del t is equal to minus h cross square by twice m del square psi by del x square plus u psi. So u is the potential operator, minus h cross square by twice m del square by del x square is p square. P cap dot p cap. P cap is momentum operator, and I h cross del by del E is energy operator, E cap. So the corresponding time independent Schrodinger equation can have the form your del square psi by del x square plus twice m by h cross square E minus u psi is equal to 0. That E is energy operator and U is your potential energy operator or potential operator or potential function. So now the complete solution can be obtained only if the boundary condition satisfied by psi is known. So let us discuss boundary condition. Then we can have two classes of wave functions. The first is wave function representing wave packets that are well localized and for which normalized integral converges. And second types are traveling harmonic wave represented by wave function that is I to the power exponential I k dot r minus omega t, in which case normalization integral diverges. So one is converges, another is diverges. The wave function belonging to the former class, that is when it is converges, represent particle if free are initially localized to a particular region of space by external forces derived from U. These describe the boundary states. The wave function belonging to the second class, that is on normalization integral diverges, represent particles which are not localized. They travel through a region under consideration from one distant part of space to another. These wave functions are useful in describing the scattering of particles by field of force. In either case, wave functions are bounded at great distances in all directions, that is psi x, when x is equal to plus minus infinite is equal to 0. Then continuity conditions. So equation 3.2 can be written in the form psi double dash x plus twice m h cross square e minus u x psi x is equal to 0. This is a second order linear differential equation. It has two linearly independent solutions for any energy capital E. Thus, if U is finite everywhere, whether or not it is continuous, a knowledge of the wave function and its derivative along the surface makes it possible to integrate the equation. This helps in finding the wave function at any point. The probability of existence of a particle cannot be spatially discontinuous. Therefore, psi x must be continuous across the boundary where ux changes abruptly. We have to further specify the boundary condition on the first derivative of psi. For the purpose, we consider a very small region of space del x located at the boundary. The change in that is psi dash is equal to d psi by dx over this region is given approximately as del psi dash is equal to d psi dash by dx del x is equal to psi double dash del x, which is equal to twice m by h cross square u minus c psi x. For a given particle, twice m by h cross square is a constant quantity. Ux and E have finite values and psi x is also finite. It means that del psi dash tends to 0 as del x tends to 0. That is, psi dash is equal to constant as long as ux is not infinite. Then we say that psi dash is continuous across the boundary. Summarizing, we say the wave function psi x is finite, continuous and single valued, and the first derivative of psi x is finite, continuous and single valued at all points where ux is finite. These requirements also have the consequence that the position probability density for a physical system is finite and continuous everywhere. Then we have general features of solutions of one-dimensional problem. The study of one-dimensional problems is significant because of two reasons. Firstly, many real problems encountered in atomic, molecular, nuclear, and solid-state physics, which are three-dimensional, can be reduced to equivalent one-dimensional problem. Secondly, various aspects of bound states and free states of a system can be understood easily from the study of one-dimensional problems. Exact analytical solution of the one-dimensional time-independent Schrodinger equation can be obtained only for a limited type of potential U. Before going to specific example, we consider some qualitative features of the solution of Schrodinger equation in a general one-dimensional potential. The time-independent Schrodinger equation for a particle of mass m and energy E moving in one-dimensional potential U is d square psi by dx square plus twice m by h cross square E minus u psi is equal to 0, or d square psi by dx square is equal to twice m by h cross square u minus e psi. The nature of the solution is dependent on the relative values of E and U. So if U is greater than E, the RHS of equation is positive. So d square psi by dx square has the same sign as that of psi. This implies that psi x is convex to the x-axis or is away from the axis as shown in the figure 3.1. If ux is smaller than E, the RHS of equation is negative and hence the sign of d square psi by dx square is opposite to that of psi. So psi x is concave to the x-axis or is towards x-axis. So two things, one is convex as shown in figure 3.1, another is concave which is shown in figure 3.2. Okay, so if U is greater than E, it is convex. If U is smaller than E, then it is your concave. Okay. So what happens then? Depending on the relative values of E and U, the solution of psi may be convex in one region and concave in other region. But the boundary condition demand that the wave function be continuous and be continuously differentiable. That is, the first derivative is continuous. So the general solution is a continuous curve satisfying the boundary condition. Now, the general features without proof of one-dimensional motion. These features will be illustrated with specific examples of potential at appropriate places. If E is smaller than U, E is smaller than U matlab convex. If E is smaller than U, the nature of the solution is shown as shown in figure 3.1, convex, but it diverges as x tends to plus minus infinite. Such a solution is not admissible if E is smaller than U everywhere. However, if E is smaller than U in some region and E is greater than U in other region, then this solution can be connected continuously. Next, if E is greater than U and E is greater than 0 or positive, the solutions are shown as shown in figure 3.2. These corresponds to free particles with wave vector k is equal to twice m root over of E by U divided by h cross. The wave vector and energy can have any continuous value. The energy spectrum is continuous. If E is greater than U and E is smaller than 0, the solution are as shown in figure 3.2. These correspond to the bound state with negative energy. The classical motion is periodic and the energy and wave vectors are constrained to have some specific allowed values. There exists at least one bound state. The spectrum of bound state is discrete. The energy eigenvalues are non-degenerate. If multiple bound states occur, they are alternatively symmetric and antisymmetric with increasing energy. Okay, these are the discussion. So, see what happens. If energy is negative, then it is it is possibility of having bound state. If energy is positive, it is free state. Then the finite potential well in bound state. A finite potential well of width 2a and depth u0 is defined by ux is equal to minus u when minus a is smaller than x is smaller than a, and is equal to 0 when modulus of x is greater than a, and it is illustrated in figure 3.3. See three regions, region 1, region 2 and region 3. In region 1 u is equal to 0, in region 3 u is equal to 0. In region 2 u is equal to u0. Am I audible? Am I audible?
Yes, sir.
Okay, ठीक है. This type of potential has sharp discontinuities at x is equal to plus minus a and cannot correspond to real physical situation. But it can provide a very useful identification for many real situations encountered in atomic and nuclear physics. Then we'll discuss Hamiltonian. The Hamiltonian of a particle of mass m moving in such a finite potential well is given by h cap is equal to px cap square by twice m plus ux cap. Acting on the configuration space wave function psi, h cap takes the form h cap is equal to minus h cross square by twice m d square by dx square plus u. Here u of minus x, that is the potential ux, is a symmetry function of x. So h cap of minus x is equal to minus h cross square by twice m d square by d of minus x square plus u of minus x, which is equal to minus h cross square by twice m d square by dx square plus ux is equal to h cap x. That is, the Hamiltonian h cap is a symmetric function of x. Then we will discuss Schrodinger equation. The eigenvalue equation h cap psi is equal to e cap psi takes the form psi double dash x plus twice m by h cross square e minus u psi x is equal to 0. For bound state e is smaller than 0, we can write e is equal to minus epsilon, where epsilon is positive. Schrodinger equation can also be written as psi double dash minus twice m by h cross square epsilon minus u psi is equal to 0. We now distinguish three different regions, 1, 2 and 3. Let the solution of equation 3.8 in these regions be psi 1, psi 2 and psi 3 respectively. Solution in region 1 and 3. In region 1, x is smaller than minus a, and in region 3, x is greater than a. In region 1 and 3, ux is equal to 0. So equation 3.8 in these regions takes the form psi 1 double dash minus k square psi 1 is equal to 0. Similarly, psi 3 double dash minus k square psi 3 is equal to 0, where your k square is equal to twice m epsilon by h cross square. Then psi 1 is equal to a1 e to the power kx plus a2 e to the power minus kx, where x is smaller than minus a. And psi 3 is equal to b1 e to the power kx plus b2 e to the power minus kx, where x is greater than a, where a1, a2, b1, b2 are arbitrary constants. The condition psi tends to 0 as x tends to plus minus infinite demands that a2 is equal to 0 and b1 is equal to 0. Then writing a1 is equal to a and b2 is equal to b, we obtain psi 1x is equal to a e to the power kx, where x is smaller than minus a, and psi 3x is equal to b e to the power minus kx, where x is greater than a. In region 2, minus a is smaller than x, smaller than a. Ux is equal to minus u0. Now equation 3.8 thus becomes psi 2 double dash plus twice m by h cross square u0 minus epsilon psi 2 is equal to 0, or psi 2 double dash minus q square psi 2 is equal to 0, where q square is equal to twice m by h cross square u0 minus epsilon. Since q square is positive, the general solution of equation 3.16 is psi 2x is equal to c sin qx plus d cos qx, where c and d are arbitrary constants, which can be evaluated by imposing the following boundary condition. Psi is continuous across the boundary. D psi by dx is equal to psi dash is continuous across the boundary. So psi 1x when x is equal to minus a is equal to psi 2x when x is equal to minus a. Similarly, psi 1 dash when x is equal to minus a is equal to psi 2 dash when x is equal to minus a. Similarly, psi 2 when x is equal to a is equal to psi 3 when x is equal to a. Similarly, psi 2 dash when x is equal to a is equal to psi 2 dash when x is equal to minus. Now, equation 3.19 and 3.20 give A e to the power minus k is equal to minus c sine qa plus d cos qa. And k e to the power minus k is equal to q c cos qa plus d sine qa. We can get equation 3.24 by differentiating both sides of this, dividing by 3.24 by equation 3.23, and we obtain k is equal to q c cos qa plus d sin qa by d cos qa minus c sin qa. Similarly, equation 3.21 and 3.22 give b e to the power minus k is equal to c sin qa plus d cos qa. Differentiating both sides, we get minus bk e to the power minus k is equal to q c cos qa minus d sin qa. Dividing equation 3.27 and equation 3.26, we get minus k is equal to q c cos qa minus d sin qa by c sin qa plus d cos qa. Solving equation 3.25 and equation 3.28, we can obtain cd is equal to minus cd or cd is equal to 0. This condition is satisfied if c is equal to 0, d is not equal to 0. And if c is not equal to 0, d is equal to 0. Accordingly, we have two classes of solution. Solutions belonging to first class. So what is the solution belonging to first class? The condition C is equal to 0 and D is not equal to 0 yields from equation 3.18. That is psi 2 is equal to D cos QX. These solutions are of even parity since psi 2, which is a function of minus x, is equal to psi 2, which is a function of x. Equation 3.28 then gives k is equal to q tan ta, q tan qa, and k is equal to qa tan qa, which is a transcendental equation. Are you getting it? Am I audible?
Yes.
Okay. The condition C is
Yes.
not equal to 0 and D is equal to 0 yields psi 2 is equal to C sin QX, which are of odd parity, as psi 2 minus x is equal to minus psi 2x. For odd parity, the sign changes. For even parity, sign do not change. Equation 3.28 then yields k is equal to minus q omega t qa, or k is equal to minus qa cot qa. This is also a transcendental equation. So both second class and first class are Am I audible? Am I audible? I think
Yes,
I'm
sir.
not audible. सुनाई दे रहा है?
Yes, sir. Yes, sir.
क्या? ठीक है. So let us continue. Then we'll discuss the solutions. Graphical solution. See, for pi by 2 smaller than r smaller than pi. See here, for pi by 2 smaller than r smaller than pi, in the figure 3.4, or pi square by 4 smaller than 2m by h cross square, u0 a square smaller than pi square, or pi square h cross square by 8m smaller than u0 a square smaller than pi square h cross square twice m. There are two bound states, one belonging to the first class and other to the second class. As u0 a square increases, more energy levels appear successively for the even class and odd class. Now, following features of the solution, let us discuss. The bound state energy eigenvalues form a non-degenerate spectrum. This is expected for any one-dimensional bound state problem. The number of bound states is finite and depends on the dimensionless parameter capital R. This in turn depends on u0 a square for a given mass. The ground state is always an even state. The next bound state are alternatively odd and even states. Then if 0 is smaller than r is smaller or equal to pi, there is one even parity bound state. If pi is smaller than r smaller than 2 pi, there are two even parity bound states. In general, there are any even parity bound states. If any minus 1 multiplied by pi smaller than r smaller than any pi. Therefore, no odd parity bound states for 0 smaller than r smaller or equal to pi by 2. There is one odd parity bound state if pi by 2 smaller than r smaller or equal to 3 pi by 2. In general, there are n0 odd parity bound states if n0 minus half pi smaller than r smaller or equal to n0 plus half multiplied by pi. Let us discuss eigenfunctions. The eigenfunctions are similar to those of infinitely deep potential well, but they penetrate slightly into the classically forbidden region where they decay to zero exponentially, as shown in figure 3.5. If we discuss infinitely deep well, then U0 tends to infinite. The result of the infinite deep well should be obtained as U0 tends to infinite, R tends to infinite. The allowed values of mu are now mu n is equal to n pi by 2, where n is equal to 1, 2, 3, so on and so forth, which gives the energy eigenvalues En is equal to h cross square pi square by 8 ma square n square. There are some examples which you can see. Okay, so this is all about potential well. So let us see what other things which are there in your syllabus. Am I audible?
Yes, sir.
Okay, okay. So simple harmony, simple one-dimensional potential one, two harmonic oscillator, spherical symmetric and hydrogen atom. So इसमें आपका है alpha decay scanning microscope, Schrodinger equation, parity, so on so forth. Schrodinger equation, quantum function. Okay. Ladder of it. Particle in a box. Particle in this. Okay. So now it free particle. We have discussed about free particle. Free particle is when potential is equal to 0. So you can derive degenerate eigenfunctions for free particle. Then your normalizable things, traveling wave as shown in figure 5.1. Then example 5, particle in a box. Similar, as we have discussed, well, the box is same. V is equal to infinite, V is equal to infinite, and in region 2, V is equal to 0. Potential function for a one-dimensional box, similar to that of one-dimensional well. Then you can solve it. Similarly, as we have discussed now, then eigenvalues and eigenfunctions. E is equal to 0, n is equal to 1, e1, n is equal to 2, e2 is equal to 4, e1, n is equal to 3, 3 is equal to 9, e1, en is equal to n square, e1. Okay. And the particle has been confined to a box, no longer have a continuous energy spectrum. The energy can take only the discrete values, and as shown in figure 5.33, equation 5.33 and figure 5.4c, figure 5.4. Okay, as shown in the screen. And this is in contrast to the classical picture in which all finite values of energy E is greater or equal to 0 are allowed. The quantization of energy follows from the boundary conditions imposed on the wave function due to the confinement of particle. Then the minimum energy of the particle in the box is not 0 but has a finite value. That is E1 is equal to pi square h cross square by 2ml square. So in quantum mechanical system, no particle can never be at rest. This is in keeping with the uncertainty principle and the concepts of 0 point energy that we must recollect. Okay, am I audible? Then the first three eigenfunction of particle in a box, psi1, psi2, and psi3. One node, so nodes are shown here. X is equal to 0, x is equal to L. The number of nodes increases as n increases. Okay. Then time dependent wave function, probability density, which I have discussed in the first class. P1, P2, P3 shown in figure 5.6. Then quantum dot. So quantum dots are sometimes called artificial atom, are typically semiconductor metal particles with size ranging from 1 to 100 nanometer. Their properties are very different from the bulk properties of materials of which they are made and depends on the size of the particle. Okay. So conductor, insulator, semiconductor, and you have studied Bohr's atomic model in an isolated atom. The electron occupy discrete energy levels, whereas in bulk materials made of several atoms, we have continuous energy bands, which are collection of available energy states and energy gaps between these bands. The quantum dot is a very tiny object. Therefore, the charge carrier inside the dot are confined within a very small region, very much like a particle in a rigid box. The simplest approximation for a quantum dot is an infinite potential well, which I am discussing now, which I have discussed earlier this class. Potential well where all the charged particles are confined. So, like a particle in a box or an electron in an atom, the charge carriers in the quantum dot occupy discrete energy levels. While in a box semiconductor material, you would have energy bands. In a quantum dot, you can encounter energy bands replaced by discrete energy levels, and it is shown in figure 5.7. Okay, valence bond, valence band, conduction band, band gap, and corresponding energy levels. Okay, absorption and emission of light by these quantum dots, as in any atom or molecule, takes place by the transition of charge carriers between these energy levels. Suppose an electron occupying the energy state J in a quantum dot of size capital D makes a transition to state I. Let us assume that the quantum dot is a one-dimensional rigid box of size D. Read the margin remark here. Ideally, you should think of an electron, so on and so forth, in page 22. Okay. Using equation 5.33 for the energy of electron, we can write the expression for energy emitted in this transition are del Eji is equal to j square minus I square h cross square pi square by twice me star d square. This energy difference depends on the size of the dot capital D. If D increases, other parameters remaining the same. The value of del Eji decreases. This is depicted in figure 5.8. Okay, energy levels variation with size for a box of size A where L1 and L2 with L1 smaller than L2, the difference between the energy levels del Eji is greater than del Eji, del dash Eji. This energy difference is emitted from the dot as a photon of light. What is the wavelength of the photon? And if the frequency of the emitted material is nu and lambda is its wavelength, where nu is equal to c by lambda, then we can write del Eji is equal to h nu is equal to sc by lambda is equal to j square minus I square multiplied by h cross square pi square by 2 me star d square. So the wavelength of the emitted photon is directly proportional to the size of the dot d. As the size of the dot increases, the wavelength of the emitted photon also increases. As d increases, even though the material of the dot may remain the same, the wavelength of the emitted light changes from the blue towards the red end of the visible spectrum. So by tuning the size of the quantum dot in the process of preparation, we can obtain a specific wavelength of emitted light. Okay. So the real quantum dot is definitely more complicated than what we have described now. However, as you can see, it is possible to understand certain salient features of light emission from quantum dots using the particle in a box model. A more realistic estimate of numbers is obtained by considering the confinement of an electron-hole pair, also called an exciton inside a spherical quantum dot. Several other applications of the quantum dot are also related to the fact that the energy levels can be tuned by its size. Quantum dots are used in single electron transistors, solar cells, LEDs, lasers, single photon sources, cell biology research, microscopy, and medical imaging. So quantum dots, sometimes called artificial atoms, are typically semiconductor or metal particles with size ranging from 1 to 100 nanometer with properties that are vastly different from the bulk material of which they are made and depend on the size of the particle. The simplest approximation for a quantum dot is an infinite potential well where all the charge carriers are confined to a region and occupy discrete energy levels like electrons in an atom. A change in the size of the dot changes changes the spacing between the energy levels. This changes the energy increased in the transition of the electron between the energy levels. So the wavelength of the light emitted by quantum dot changes with the size of the dot. Okay. Then you see here step potential and Schrodinger equation. Step region 1 and region 2. In region 1, V is equal to 0. In region 2, V is equal to V0. Okay. Then your the picture, the particle with energy is incident from region 1 and subjected to step potential V0 at x is equal to 0. We consider two cases, when E is smaller than V0 and when E is greater than V0. Okay. Am I audible? Am I audible?
Yes, sir.
Okay, okay. So potential step. Is the screen visible?
Yes, sir.
Okay. Then for step, your a part is reflected, part is transmitted, as shown in figure 5.13. See, a e to the power I k1x is the incident wave. Then after incidence, one is reflected, b e to the power minus I k1x, and one is transmitted, f e to the power I k2x, as is resulted from the solutions. Okay. Then as one some part is reflected and part is transmitted, there is a reflection and transmission coefficient, as you had already seen in your electromagnetic wave scenario. That is R is equal to modulus of JR by JI is equal to modulus of B square by modulus of A square is equal to K1 minus K2 by K1 plus K2 square. Similarly, we can determine the transmission coefficient capital T using the equations. 2A is your 5.58. That is this. T is equal to modulus of Zt by Ji, and R is equal to modulus of B square by A square. Okay, reflection coefficient and transmission coefficient. Then your T can be written as 4K1 K2 by K1 plus K2 square. Okay. Then there are some more one-dimensional problems we can discuss. There are some problems given in your course material. One-dimensional barrier, one-dimensional potential barrier. This is very similar to that of potential step, and you can see it in figure 6.1. And you can solve the Schrodinger equation for region 1, region 2, and region 3. And you have energy of the particle for E is smaller than V0. V0 minus E is positive, and solution with real values of the parameter K, and energy of the particle is greater than V0. You have psi in region 2 is equal to CE to the power I alpha x plus d to the power minus I alpha x, and your alpha is equal to root over of twice m E minus V0 by h cross square. Then for in case 1, E is smaller than V0, and in case 2, you have the different scenario. Is case 1, for E is smaller than E0, we can determine the constant A, B, C, D. Okay. And you can solve in different regions, and you have the wave function for the one-dimensional potential barrier or a particle with an energy less than that of the barrier height can be shown in the picture 6.3. Psi, then after the barrier comes, then it is transmitted with a less amplitude, smaller amplitude. The probability density as a function of position for a quantum mechanical particle with an energy less than the barrier height. Okay, so 6.3, your classical picture, and 6.4, your quantum mechanical picture. Then here also you have reflection and transmission coefficient, incident wave A to the power ikx, and reflected wave B to the minus ikx, and transmitted wave F e to the power ikx. And your R is equal to root over modulus of B square by modulus of A square. R is equal to modulus of B square by modulus of A square. Your transmission coefficient T is equal to modulus of F square by modulus of A square. So these are the things, and your R plus T is equal to 0. Reflectance plus transmittance is equal to unit, that is 1. The transmission coefficient tells us about the extent of penetration of the barrier by the particle. So it can also be called tunneling probability. Okay. So this phenomena is called barrier penetration. It penetrates through the barrier. And wide barriers, large values for B0, you can have the equation 6.25 and 26. And tunneling length, you can calculate lambda T is equal to 1 by K dash is equal to H cross by root over of twice m V0 minus E. Okay. So transmission coefficient can also be written in the form 16 E by V0, 1 minus E by V0 e to the power twice L by lambda T for L by lambda T greater, very, very greater than 1. There are some examples 6.1, 6.2, so on and so forth. Then your 6.2.3, reflection and transmission coefficient for E is greater than V0. Okay, the typical variation of reflection coefficient capital R and transmission coefficient capital T with E by V0 for twice M V0 L square by H cross square is equal to 16 is shown in figure 6.6. Then we have many applications of quantum tunneling. One is alpha decay. All alpha particles emitted from the same source have almost the same kinetic energy. If they are emitted from different source, the kinetic energy lie within a narrow range 4 to 9 mega electron volt. The half-life of the radioactive elements from which the alpha particle is emitted, however, varies over a very large range. For example, the half-life of polonium 214 is 160 microsecond and the half-life of uranium 238 is around 4.5 billion years. Incidentally, the kinetic energy of the emitted alpha particles are minus 7.7 mega electron is equal to 7.7 mega electron volt of the order of 7.7 mega electron volt for polonium and 4.3 mega electron volt for uranium. So the large variation in half-life of the parent element in the alpha decay process was explained by George Gamow using the concept of quantum tunneling. So quantum tunneling can be used for explaining this alpha decay. And you have T is equal to E to the power minus 2 K dash L is equal to E to the power minus 2 root over of R0 to R E to the power minus 2 integration R0 to R root over of twice M by H cross square VR minus E dr. So this tunneling probability T is the probability of emission of an alpha particle from a nucleus. T is used to calculate the decay rate lambda for the nucleus, which is the alpha particle emission probability per unit time. We can calculate lambda and we multiply T by the number of times the alpha particles approaches the barrier per second. The number is just V by 2R0, where V is the speed of alpha particle inside the nucleus, and V can be calculated from the kinetic energy E of the alpha particle when it escapes from the nucleus. Now your V by 2R0 is nearly equal to 10 to the power 21 collisions per second, and decay rate lambda is equal to 10 to the power 21 T. And this concept, the quantum tunneling, is used also in scanning tunneling microscope, STM. And the picture, how physically it happens, is shown in figure 6.8. And one-dimensional finite potential well, as shown in figure 6.9. Then you can solve Schrodinger equation, and there are some examples. Then we'll discuss parity of eigenfunctions. Finite well potential function defined by equation 6.34 is symmetric. That is V, which is a function of x, is equal to V, which is a function of minus x. So Vx is equal to V of minus x. So as we have learned by solving example 3.3, 6.3, which I was showing now, the Hamiltonian H cap of the symmetric potential well commutes with the parity operator P cap. Now, if we recollect the results of the examples, you can see if an operator A cap commutes with the parity operator P cap, then the non-degenerate eigenfunctions of A cap have a definite parity. That is, they are either of odd parity or of even parity. So the solution of the Schrodinger equation for the symmetric finite potential well, which are the eigenfunctions of H cap, will have a definite parity. That is, the eigenfunctions will either be even or odd. Okay. So for region 2, it is either A or B should be 0. Okay. Similarly, you can find that C is equal to A for some even parity and C is equal to minus A for odd parity. So you can also derive energy eigenfunctions and C R is equal to root over twice m v0 s square by h cross square. The energy eigenvalues can be obtained by solving this for eta and xi for a fixed value of r. Now combining the equation, we can write eta square plus xi square is equal to r square, and eta is equal to xi tan xi when eta and xi greater than 0 for even parity states. Now you can see graphical solution for this also, as we have discussed graphical solution for potential well. And these are the discussions. You can go through the course material of IGNU, then symmetric infinite potential well, which I have discussed earlier in this class, and the eigen functions, how they are symmetric, and the discussion. So these are the examples. You can go through the IGNU material. And how to calculate reflection and transmission coefficient is given in appendix 6A. Then we'll discuss simple harmonic oscillator. Shall I take a break for you? After that, we'll start the next class. Or shall I continue? Anybody? Am I audible? Am I audible?
Sir.
So shall I continue, or you
Yes,
need
sir.
a
Please continue.
break? Huh?
Please continue, sir.
Okay,
Sir,
okay.
continue, sir.
Okay, you need not have any break. Okay, ठीक है. I shall continue. So next we will discuss linear harmonic oscillator. I think the screen is visible.
Yes, sir.
Okay. Linear harmonic oscillator is nothing but simple harmonic oscillator type of thing. A linear harmonic oscillator or simple harmonic oscillator is a point particle attracted towards a fixed center by a force proportional to the displacement of the particle from the fixed center, as shown in figure 3.6. You see in the middle of the figure, and you know it in your BSc classes. So you have, and now we can have the quantum mechanical solution of this type of problem. If the motion is chosen along the x-axis, that is one dimensional, with the origin at the force center, and then the force is given by F vector is equal to minus k x vector, and which is equal to minus x cap du by dx, where k is the force constant and u is the potential energy function. So u can be written as half kx square is equal to half m omega square x square, where k is equal to m omega square. So here your m is the mass of the oscillating particle and omega is the angular frequency of the oscillation. So you can write ux is equal to u of minus x. The potential energy function is a continuous and symmetry function of x. The plot of ux, which is nearly equal to x, is shown in figure 3.6. Now, the Hamiltonian of the oscillating particle is h cap is equal to p cap square by twice m plus half m omega square x cap square. It has the property h cap of minus x is equal to h cap of plus x. That is, the Hamiltonian for the oscillator is a symmetry function of x. The time independent Schrodinger equation for the oscillator is minus h cross square by twice m d square psi by dx square, d square psi by dx square plus half m omega square x square psi is equal to E psi, energy operator E. So we can have the eigenvalue equation and its solution. The eigenvalue equation h cap psi is equal to E cap psi for the oscillator takes the form psi double dash plus twice m by h cross square multiplied by E minus half m omega square x cross square x square psi is equal to 0. So you can write it as psi dash plus twice m E by h cross square minus m square omega square by h cross square whole multiplied by x square psi is equal to 0. The eigenvalues and eigenfunctions of the oscillator can be obtained by solving this. In order to achieve this, we have to introduce a dimensionless variable y is equal to m omega by h cross to the power half x. Then we have d by dx is equal to dy by dx, d by dy is equal to your m omega by h cross to the power half or m omega by h cross root over d by dy. And your d square by dx square is equal to d by dx, d by dx is equal to m omega by h cross d square by dy square. Now substituting these values in equation 3.40, that is psi double dash plus 2a twice m e by h cross square minus m square omega square x square by h cross square psi is equal to 0. If we put this, then we can get m omega by h cross psi double dash plus twice e by h cross omega minus y square psi is equal to 0. Now, as m omega by h cross is not equal to 0, the eigenvalue equation reduces to psi double dash plus lambda y square psi is equal to 0. Now we have lambda is equal to twice e by h cross omega. Now, before attempting for the complete solution of equation 3.42, we analyze the behavior of the solution in the asymptotic region. A modulus of y is tends to infinite. So now if we discuss the asymptotic behavior of psi, we can have if y tends to infinite, y square is very greater than lambda, and for any finite value of e, the dimensionless variable lambda is negligible in comparison with y square. So we can have the equation 3.42 as psi infinite second derivative of psi infinite is equal to y square psi infinite is equal to 0. So second derivative of psi infinite minus y square psi infinite is equal to 0. Let psi infinite is equal to e to the power beta y square be a trial solution of this equation. So you can have psi infinite dash is equal to 2 beta y e to the power beta y square. Am I audible?
Yes, sir.
Okay. So psi infinite double dash is equal to twice beta e to the power beta y square multiplied by 1 plus 2 beta y square, which is nearly equal to 4 beta square y square e to the power beta y square. Now the equation will become 4 beta square minus 1 multiplied by y square e to the power beta y square is equal to 0. So you have 4 beta square minus 1 is equal to 0, or beta is equal to plus minus half. So you have psi infinite is nearly equal to e to the power plus minus half y square. The solution must be finite everywhere and satisfy psi infinite tends to 0 as y tends to plus minus infinite. But the solution with positive exponent psi infinite nearly equal to e to the power half y square diverges as y tends to infinite and is not acceptable. So the general acceptable solution of this equation is of the form psi is equal to f of y e to the power minus y square by 2, where f of y is to be determined. The function f of y should be such that it does not affect the asymptotic behavior of psi. Now you have psi dash is equal to f dash minus yf e to the power minus y square by 2, and psi double dash is equal to f double dash minus 2y f dash minus f plus y square f multiplied by e to the power minus y square by 2. Now substituting these two into equation 3.42, 3.42, that is psi double dash plus lambda minus y square psi is equal to 0. You can have f double dash minus twice y f dash plus lambda minus 1 f multiplied by e to the power minus y square by 2 is equal to 0. So you have f double dash minus 2y f dash plus lambda minus 1 f is equal to 0. You can solve it by power series, which I was discussing yesterday. The solution of the differential equation can be written in form of the general equation, that is, you can take the power series f of y is equal to summation s is equal to 0 to infinite as y to the power s, then first derivative summation s is equal to 1 to infinite as y to the power s minus 1, then f double dash is equal to summation s is equal to 2 to infinite s into s minus 1 as y to the power s minus 2. Okay, so how can you solve it? Now put these two values in the general form of power series, and you can have the lowest power का जो होगा कोएफिशिएंट, उससे आपको इंडिशियल इक्वेशन मिलेगा, और जो हाईएस्ट पावर होगा उससे आपको रिकरेंस रिलेशन मिलेगा, और इंडिशियल इक्वेशन से आपको मिलेगा द वैल्यू ऑफ योर एस. सो एस का वैल्यू पुट करने से केस 1 केस 2 से आप रिकर्सन रिलेशन से आपको सोल्यूशन मिलेगा. तो दीज आर द थिंग्स यू सी हियर व्हिच आई वाज डिस्कसिंग यस्टरडे. So by solving this in power series, you can have your lambda is equal to 2n plus 1 when n is equal to 0, 1, 2, so on and so forth. And en is equal to n plus half h cross omega, where n is equal to 0, 1, 2, so on and so forth. And your E0 will be half h cross omega, and U1 is equal to 3 by 2 h cross omega, and E2 is equal to 5 by 2 h cross omega, so on and so forth. And your En minus 1 is equal to h cross omega for all n. Now, this can be expressed at energy eigenvalues and eigenfunctions. Okay. So by substituting lambda is equal to 2n plus 1 in equation 3.47, we can get f double dash minus 2y f dash plus 2n f is equal to 0. And this is nothing but Hermite differential equation. And you know how to solve a Hermite differential equation. I have told you yesterday. Are you getting it, Indranil ji? Am I audible?
Yes, sir.
Yes, sir.
ओके ओके ओके. कल मैं बोल रहा था ना, आप पूछ रहे थे कि इसका यूज कहाँ होगा. आज आ गया 2-3 यूज, देखिए.
हाँ हाँ.
ठीक है कनक ज्योति जी, कल पूछ रहे थे ना आप लोग.
जी जी.
ठीक है, ये देखिए कब कहाँ कहाँ यूज होता है. वहाँ एक पावर सीरीज हमने यूज किया, यहाँ एक हर्माइट पॉलिनोमियल यूज हो रहा है. ठीक है इंद्रानील जी, कनक ज्योति जी.
बिल्कुल सर, थैंक यू.
ठीक है. सो एफ इज इक्वल टू एच एन इज इक्वल टू माइनस 1 to the power n e to the power y square d to the power n by d to the power n e to the power minus y square by dy to the power n. ओके, ये क्या है? ये जो एच एन वाई हमने लिखा है, याद आ रहा है कल जो पढ़ा रहा था?
जी।
क्या है ये? कल मैं दिखा रहा था ना कैसे हर्माइट पॉलिनोमियल आप सॉल्यूशन से भी निकाल सकते हैं और किससे निकाल सकते हैं। दो चीज से बोला था ना, सॉल्यूशन से भी आप निकाल सकते हैं और किससे निकाल सकते हैं।
नोट देखना है सर। थैंक यू
मैं कल
सर।
पढ़ा रहा था रोड्रिगो फार्मूला, जनरेटिंग फंक्शन, ये सब पढ़ा रहा था
जनरेटिंग
ना।
फंक्शन, हाँ जनरेटिंग
इससे
फंक्शन,
हम
हाँ।
H0 H1 H2 निकाल सकते हैं अपार्ट
लास्ट
फ्रॉम योर
लास्ट नोट में
सॉल्यूशन।
पढ़ा रहता है, जनरेटिंग फंक्शन पढ़ा है।
हाँ, तो उसको जब पढ़ाने जो आपने सर्कुलेट कर दिया ना बाकी लोगों से नोट,
आई हैव
जितने कल क्लास में थे।
सर्कुलेट कर दिए हैं। आप 4 फाइल दिए
हाँ,
थे, चारों फाइल सर्कुलेट कर दिए।
ठीक है ठीक है। सो आप देख लीजिए अब इस क्लास खत्म होने के बाद, ठीक है। और इससे भी हम निकाल सकते हैं डिफरेंट रिकर्सन रिलेशन एंड अदर थिंग्स एंड H0 H1 सो ऑन सो फोर्थ। तो जब निकालेंगे यहाँ हम दिखा रहा हूँ, देखो HN+2 इज इक्वल टू 2y HN+1 माइनस 2n+1 HNy and your orthonormality condition is integration minus infinite to infinite HN HM e to the power minus y square dy is equal to 2 to the power n factorial root over pi del mn. So the eigenfunctions of harmonic oscillator can be expressed as psi n, which is a function of y, is equal to n HNy e to the power minus y square by 2, where Hn is your what? Hermite what? Hermite polynomial, ठीक है। And your psi n is equal to n Hn, which is a function of alpha x e to the power minus half alpha square n square alpha square x square, ठीक है। Where alpha is equal to root over of m omega by h cross and y is equal to alpha x and n are normalization constant, which can be determined using the normalization condition which I was discussing yesterday. What is the normalization condition? Integration minus infinite to infinite psi n star psi n dx is equal to 1, which is equal to modulus of n square integration minus infinite to infinite hn star alpha x hn alpha x e to the power minus alpha square x square dx. And this is equal to modulus of n square by alpha integration minus infinite to infinite hn star hn e to the power minus y square dy is equal to n modulus of n square by alpha pi to the power alpha 2 to the power n factorial. So your n is equal to alpha by 2 to the power n factorial root over pi to the power minus half or its root over. So the energy eigenfunctions of harmonic oscillator can be written as psi n is equal to alpha 2 to the power n factorial root over pi to the power half hn alpha x e to the power minus alpha square x square by 2. Now yesterday I was shown you how you can derive h0 is equal to 1, h1 is equal to 2y, h2 is equal to 4, y square minus 2, h3 is equal to 8, yq by 12y, etc. Yesterday I was written in form of x, now you can see it in form of y. Now the eigenfunctions corresponding to n is equal to 0, 1, 2, 3 states are psi 0 is equal to alpha by root over pi to the power half e to the power minus alpha square x square by 2. Psi 1 is equal to alpha by 2 root over pi to the power half 2 alpha x e to the power minus alpha square x square by 2. Psi 2 is equal to alpha by 8 root over pi to the power half 4 alpha square pi square minus 2 e to the power minus alpha square x square by 2. Similarly, psi 3 is equal to alpha by 48 to the root over of pi to the power half 8 alpha q x q minus 12 alpha x e to the power minus alpha square x square by 2. Okay. Then you can have the energy level diagram of these wave functions. According to this equation, only certain energy values are determined by quantum numbers n are allowed. For n is equal to 0, the energy eigenvalue is E0 is equal to half h cross omega. See here. E0 is equal to half h cross omega, and it is shown in this picture. E0 is equal to half h cross omega. Okay. Similarly, E1 is equal to 3 by 2 h cross omega, E2 is equal to 5 by 2 h cross omega, E3 is equal to 7 by 2 h cross omega. E4 is equal to 9 by 2 h cross omega. You see, there are two things you can see in this figure 3.7. E0 is equal to half h cross omega. What do we conclude from it? Anybody? Am I audible?
Yes, sir, you are audible.
देखो E0 जो है हाफ h cross omega, it is not zero. So the minimum value energy is non-zero. क्लासिकली आप क्या एक्सपेक्ट करते हैं? जब आपका कोई पार्टिकल ऑसिलेट करता है, वो क्यों ऑसिलेट करता है? बिकॉज ऑफ योर टेम्परेचर और थर्मल एनर्जी. When you reduce the energy, it gradually its oscillation diminishes, and at absolute zero you have the particle is at rest. There is no oscillation. Classically, this picture is expected. Am I right or wrong? Suppose आपका 95 डिग्री में वाटर को आप रखेंगे, तो the particle will be very much energetic, and it will move, oscillate or move with a high frequency. When you reduce it 35 डिग्री 25 डिग्री आइस जब आ जाएगा, फिर क्या होगा? धीरे धीरे वो सॉलिड स्टेट में आ जाएगा. और अगर कोई भी पार्टिकल आप लो, चाहे आप वाटर मॉलिक्यूल लो, चाहे आप नाइट्रोजन लो, चाहे हाइड्रोजन लो, चाहे एनीथिंग you can take at absolute zero. What you expect from classical mechanics? Anybody? You forget. At zero, you expect the energy must be zero. Am I right or wrong? Am I audible?
Yes, sir, you are audible.
So at absolute zero, you expect energy must be zero. But here in quantum mechanical case, you see E0 is not equal to zero. It is half h cross omega. So zero, the minimum energy of a harmonic oscillator, if you go through a quantum mechanical solution, quantum mechanical approach, is non-zero. That is half h cross omega. And this energy, half h cross omega, is called 0 point energy. At zero, the energy is not zero. It has some value. And this value is called 0 point energy. And another thing you can see, E1 minus E0, 3 by 2 minus half, is equal to how much? H cross omega. Then your E2 minus E1, 5 by 2 minus 3 by 2, is equal to how much? H cross omega. Then E3 minus E2, 7 by 2 minus 5 by 2, how much? H cross omega. समझ में आ रहा है? 7 by 2 minus 5 by 2 or multiplied by h cross omega. 7 minus 5 by 2 h cross omega. 2 by 2 h cross omega is equal to h cross omega. Similarly, E4 minus E3, 9 by 2 minus 7 by 2 h cross omega is equal to h cross omega. So they are equispaced. In harmonic oscillator, the energy levels are equispaced, and the minimum energy is not zero. It has some finite value. So it is called 0 point energy. Okay. So this is the discussion. And if you del En by En is equal to 2 by 2n plus 1 is equal to 1 by n plus half. When n is large, del En by En is nearly equal to 1 by n. When n tends to infinite and del En tends to 0, it implies that states with large n are separated by an interval that is small compared to the total energy of those states, and the classical result is thus approached. Then the existence of 0 point energy implies that the particle in the oscillator well cannot be at rest at the equilibrium position. The 0 point energy can be shown as a necessary consequence of uncertainty principle. कैसे ये अनसर्टेनिटी प्रिंसिपल कैसे आप बोल सकते हैं? अनसर्टेनिटी प्रिंसिपल क्या बोलता है? The product of two canonical conjugate variables is having some value h by 2 या बोलो या greater or equal to h by 2, इस तरह से बोलता है. That means you cannot in absolute precision measure either the position, both the position and momentum of an particular object. So agar you measure momentum with absolute, if you measure momentum with absolute accuracy, your position measurement will be less accuracy. And if you measure in the reverse way, the other will be in less accuracy. So when the particle will oscillate, then you cannot measure your del x with accuracy. And that means अगर आप रेस्ट हो गया, then इसका मोमेंटम का जो है at the equilibrium position, it cannot be at rest. Then energy eigenfunction psi 0 is equal to alpha by root over pi to the power half e to the power minus half alpha square x square, where E0 is equal to half h cross omega, where E1 is equal to 3 by 2 h cross omega. You have psi 1 alpha by 2 root over pi to the power half 2 alpha x e to the power minus half alpha square x square, so on and so forth. Okay. Now you see psi n x is equal to psi n x if n is even. And psi n minus x, sorry, psi of minus x, psi n minus x is equal to psi n of x if n is even, and psi n of minus x is equal to minus psi n of x if n is odd. So this is all about parity operation. So the eigenfunctions of harmonic oscillators are having definite parity. अगर हम माइनस एक्स लेंगे दूसरा वैल्यू आता है, इवन होता है तो, और ऑड होता है तो दूसरा वैल्यू होता है, तो यह पैरिटी भी जो है यहाँ दिखाई देता है. The ground state wave function psi 0 has no node. See in picture 3.10. It is a Gaussian function of x. The first excited state psi 1 has no node. The second excited state psi 2 has two nodes. See picture figure 3.10. So in general, the wave function of n state has n nodes. The energy levels wave function psi x and their probability densities psi modulus of psi square for the first four states are presented in figure 3.8 and 3.9 respectively. The intersection of probability curves with the potential curve u gives the classical limit of oscillation. Thus, there is finite probability of observing the particle outside the classical limit of the oscillation. The probability density for the harmonic oscillator in the n is equal to 11 state is shown in figure 3.10. See. So there are some examples. You can go through it. Then we'll discuss the next part, quantum theory of hydrogen-like atom. Before that, let us discuss angular momentum operator in Cartesian coordinates. Am I audible?
Yes, sir.
Okay. The angular momentum operator can be derived from the linear momentum operator using the relation L vector is equal to R cross P, cross product. In terms of components, the above relation may be written like that. L vector is equal to I cap, J cap, K cap, X, Y, Z, Px, Py, Pz. So you have Lx is equal to Ipz minus Zpy, Ly is equal to Zpx minus Xpz, and Lz is equal to Xpy minus Ypx. So you have Lx cap is equal to I cap, Pz cap minus Z cap, Py cap. Similarly, Ly cap is equal to Z cap, Px cap minus X cap, Pz cap. Lz cap is equal to X cap, Py cap minus Y cap, Px cap. Substituting the values of the position operator and the linear momentum operator in the equation, we get the corresponding angular momentum operators as Lx cap is equal to Y minus IH cross del by del Z minus Z into IH cross del by del Y. Then Lx cap is equal to minus IH cross Y del by del Z minus Z del by del Y. Similarly, Ly cap is equal to minus IH cross Z del by del X minus X del by del Z. Similarly, Lz cap is equal to minus IH cross X del by del Y minus Y del by del X. So, these are the angular momentum operators in Cartesian coordinates. Then angular momentum operator in spherical polar coordinates. The angular momentum operator in spherical polar coordinates r, theta, phi can be derived from the respective operators in Cartesian coordinates x, y, z using the following relation. X is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. The inverse relation can be written as r is equal to root over of x square plus y square plus z square, and cos theta is equal to z by r, and tan phi is equal to y by x. Now expression for del by del x, del by del y, del by del z in terms of r, theta and phi, you have to consider the function u is equal to u, which is a function of r, theta and phi. So according to chain rule, the partial differentiation, chain rule of partial differentiation, we can have del u by del x is equal to minus del u by del r multiplied by del r by del x plus del u by del theta by del x plus del u by del phi by del x. Now differentiating this with respect to x, we can have 2r del r by del x is equal to 2x. So you have del r by del x is equal to x by r is equal to r sin theta minus cos phi by r sin theta multiplied by cos phi. Differentiating with respect to x, we have sec square phi del phi by del x is equal to minus y by x square is equal to minus r sin theta multiplied by sin phi divided by r sin theta cos phi square. So del phi by del x is equal to r sin theta sin phi divided by r sin theta cos phi multiplied by 2 sec square phi. You have minus sin phi by r sin theta. Now differentiating with respect to x, we have minus sin theta del theta by del x is equal to minus z by r square del r by del x is equal to minus z by r square sin theta cos phi, which can be written as minus r cos theta sin theta cos phi by r square sin theta is equal to cos theta cos phi by r. Substituting the values from equation 4.9, 4.10 and 4.11 in equation 4.8, we can get del u by del x is equal to sin theta cos phi del u by del r plus cos theta cos phi by r del u by del theta minus sin phi by r sin theta del u by del phi. Then we have sin theta cos phi del by del r plus cos theta cos phi by r del by del theta minus sin phi by r sin theta del by del phi. So you have del by del x is equal to sin theta cos phi del by del r plus cos theta cos phi by r del by del theta minus sin phi r sin theta del by del phi. Similarly, the chain rule for partial differentiation with respect to y and z, we can have del by del y is equal to sin theta sin phi del by del r cos theta sin phi by r del by del theta plus cos phi by r sin theta del by del phi. So you have del by del z is equal to cos theta del by del r minus sin theta by r del by del theta. Now components Lx of the orbital angular momentum in terms of spherical polar coordinates can be written as Lx cap is equal to minus IH cross y del by del z minus z del by del y. Substituting the values of equation 4.4, 4.13 and 4.14 in the above equation, we get Lx cap is equal to minus IH cross r sin theta sin phi cosine theta del by del r minus sin theta by r del by del theta minus r cos theta sin phi del by del r plus cos theta sin phi by r del by del theta plus cos phi r sin theta del by del phi. So you have Lx cap is equal to minus IH cross r sin theta sin phi cos theta del by del r minus sin square theta sin phi del by del theta minus r cos theta sin phi del by del r minus cos square theta sin phi del by del theta minus cos theta cos phi by sin theta del by del phi. So you have Lx cap is equal to minus IH cross minus sin square theta sin phi del by del theta minus cos square theta sin phi del by del theta minus cos theta cos phi sin by sin theta del by del phi. So you have minus IH cross minus sin square theta plus cos square theta multiplied by sin phi del by del theta minus cos theta cos phi by sin theta del by del phi. So you have Lx cap is equal to IH cross sin phi del by del theta plus cos theta cos phi by sin theta del by del phi. So components of Ly of the orbital angular momentum in terms of spherical polar coordinate system can be written as the y component of angular momentum operator in Cartesian coordinates can also be written as Ly cap is equal to IH cross z by z multiplied by del z minus x multiplied by del z. Now substituting these values from equation 4.4, 4.12, 4.14 in the above equation, we can get Ly cap is equal to minus IH cross r cos theta sin theta cos phi del by del r plus cos theta cos phi by r del by del theta minus sin phi r sin theta del by del phi minus r sin theta cos phi multiplied by cos theta del by del r minus sin theta by r del by del theta is equal to minus IH cross r cos theta sin theta cos phi del by del r plus cos square theta cos phi del by del theta minus cos theta sin phi by sin theta del by del phi minus r sin theta cos phi del by del r plus sin square theta cos phi del by del theta. So Ly cap is equal to minus IH cross cos square theta cos phi del by del theta plus sin square theta cos phi del by del theta minus cos theta sin phi by sin theta del by del phi. So you can write Ly cap is equal to minus IH cross cos phi del by del theta minus cos theta sin phi by sin theta del by del phi. Now components of Lz of the orbital angular momentum in terms of spherical polar coordinate system can be written as like this. The z component of angular momentum operator in Cartesian coordinate system can be written as Lz cap is equal to minus IH cross x by del y, x del by del y minus y del by del x. Now substituting the values from equation 4.4, 4.12, 4.13 in the above equation, we can
Good
write
evening, sir. Sir, which course code is this? I joined later in this class.
this is quantum mechanics. ठीक है, physics का quantum mechanics 1 है.
Okay, sir. Sir, which topic is this?
इसे हाइड्रोजन एटम डिस्कशन करने के लिए जो इनिशियल चीज है उसको हम डिस्कस कर रहे हैं. कैसे स्फेरिकल पोलर कोऑर्डिनेट सिस्टम, कार्टेशियन कोऑर्डिनेट सिस्टम में सिमेट्रिकल फंक्शंस को हम लिख सकते हैं. ठीक है.
Okay, sir.
Then Lz cap can be written as minus IH cross del by del phi. Then square of the orbital angular momentum, L cap square is equal to minus S cross square, minus S cross square 1 by sin theta del by del theta of sin theta del by del theta 1 by sin square theta del square by del phi square. This can be written from the expression L cap square is equal to Lx cap square plus Ly cap square plus Lz cap square. Okay. So this is the general expression. Now you can see how Schrodinger equation behaves in spherical symmetric potential. So you know Schrodinger equation can be written like this: del square psi plus twice m h cross square E minus U psi is equal to 0 in 3 dimensions. So the picture is like this. Figure 4.1. Now you have x is equal to r sin theta cos phi, y is equal to, x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, z is equal to r cos theta. So you have x square plus y square plus z square is equal to r square, and r is equal to root over of x square plus y square plus z square. Now your tan phi is equal to y by x, and tan theta is equal to root over of x square plus y square by z. Now using the equation 4.20 and 21, now which I have discussed, we can write these expressions. Del r by del x is equal to sin theta cos phi, del theta by del x is equal to cos theta cos phi by r, del r by del y is equal to sin theta sin phi, del theta by del y is equal to cos theta cos sin phi by r, del r by del z is equal to cos theta, del theta by del z is equal to minus sin theta by r. Okay. So you have del phi by del x is equal to minus sin phi by r sin theta, del phi by del y is equal to cos phi by r sin theta, del phi by del z is equal to 0. So you can write del psi by del x is equal to del psi by del r by del x plus del r by del theta by del x, then plus del psi by del phi by del x. So you can write it as sin theta cos phi del psi by del r plus cos theta cos phi by r del psi by del theta minus sin phi r sin theta del psi by del phi. So you can write del by del x is equal to sin theta cos phi del by del r plus cos theta cos phi by r del by del theta minus sin theta by r sin theta del by del phi. Now del square psi by del x square is equal to del by del x del psi by del x. So you can write sin theta cos phi del by del r plus cos theta cos phi by r del by del theta minus sin phi r sin theta del by del phi multiplied by sin theta cos phi del psi by del r plus cos theta cos phi by r del psi by del theta minus sin theta by r sin theta del psi by del phi. Similarly, you can write del psi by del y, del square psi by del y square as shown in the screen. Now you can also write del psi by del z as cos theta del psi by del r minus sin theta by r del psi by del theta, so that del by del z is equal to cos theta del by del r and minus sin theta by r del by del theta. And you can write del square psi by del z square is equal to del by del z del psi by del z, which is equal to cos theta del by del r minus sin theta by r del by del theta multiplied by cos theta del psi by del r minus sin theta by r del psi by del theta. Now adding and simplifying these expressions, you can write del square psi is equal to del square psi by del x square plus del square psi by del y square plus del square psi by del z square, well, del is your Laplacian operator. So this can be written as 1 by r square del by del r multiplied by r square, 1 by r square del by del r of r square del psi by del r plus 1 by r square sin theta del by del theta of sin theta del psi by del theta plus 1 by r square sin square theta del square psi by del phi square. Now substitute this in equation, original equation. Now the Schrodinger equation for spherically symmetric potential in a spherical polar coordinate system can be written as 1 by r square del by del r of r square del psi by del r plus 1 by r square sin theta del by del theta of sin theta del psi by del theta plus 1 by r square sin square theta del psi by del phi square plus twice m by h cross square E minus U psi is equal to 0. So from this equation, you can solve hydrogen-like problem or hydrogen atom problem. See here, equation 4.28. The 4.27 को हमने 4.28 में कैसे लिखा? फिर आगे चलो, म्यू क्या होगा? अब रिड्यूस मास, ई क्या होगा? एनर्जी ऑफ द पार्टिकल, ई क्या होगा? एनर्जी ऑफ द पार्टिकल, यू क्या होगा? Potential energy of the electron, that is minus E square by R. One electron system, so E square by R, where R is the atomic radius. In order to solve the equation, now express psi as the product of three functions, that is R, phi and theta. Okay, हम जो पहले क्लास में जो आपको बता रहे थे, कोई पार्शियल डिफरेंशियल इक्वेशन होगा, उसको आपको लीनियर ऑर्डिनरी डिफरेंशियल इक्वेशन से कैसे कन्वर्ट करेंगे? बाय सेपरेशन ऑफ वेरिएबल मेथड. हियर वही कर रहे हैं, साई को हम वेरिएबल सेपरेशन कर रहे हैं आर, थीटा एंड फाई में. ओके, एंड इट इज शोन इन द स्क्रीन. अब साई इज इक्वल टू आर व्हिच इज अ फंक्शन ऑफ आर, थीटा व्हिच इज अ फंक्शन ऑफ थीटा एंड फाई व्हिच इज अ फंक्शन ऑफ फाई. नाउ सब्स्टिट्यूट, you know how to solve by separation of variable, and so and see in the screen I have done what I have taught in your first class of mathematical physics, and the result will be now come to the result. तीन सॉल्यूशन आएगा. पहले वाला होगा फाई इक्वेशन. फाई सॉल्यूशन जो होगा फाई एम व्हिच इज अ फंक्शन ऑफ फाई इज इक्वल टू 1 बाय रूट ओवर पाई ई टू द पावर आई एम फाई. ओके, अब m is equal to 0 plus minus 1 plus minus 2 plus minus 3 and so on so forth, and it is called as magnetic quantum number. Then theta equation को जब सॉल्व करेंगे तो क्या मिलेगा? x को cos theta ले लो, then del by del x 1 minus x square del theta by del theta plus beta minus m square by 1 by minus x square theta is equal to 0. This is the standard equation. So we must have beta is equal to L multiplied by L plus 1. Where L is equal to 0, 1, 2, 3 and it's called the azimuthal quantum number. Okay, फर्स्ट वाला क्या हो गया आपका? मैग्नेटिक क्वांटम नंबर. अभी जो आया है आपका फाई सॉल्यूशन से, अब थीटा सॉल्यूशन में आया है आपका क्या? अजीमुथल क्वांटम नंबर. क्या याद आ रहा है? बोर्स एटम में हम जो आप लोग जो पढ़े थे बीएससी में. Am I audible? Am I audible?
Yes, sir.
Okay. Now the solution of the equation may be written as theta equation जो लेंगे उसमें ml रहेगा, which is a function of theta, is equal to root over of 2l minus 1 by 2 multiplied by l minus modulus of m factorial by l plus m factorial whole multiplied by pl, so p subscript l superscript modulus of m cosine of theta, which is a function of cosine of theta, and plm is called the associated Legendre function. एसोसिएटेड लीजेंडर फंक्शन. हम जब डिस्कस कर रहे थे स्पेशल फंक्शंस, उसमें एक एसोसिएटेड लीजेंडर फंक्शन था जो आपके कोर्स में नहीं था, इसलिए हमको ज्यादा डिटेल हमने डिस्कशन नहीं किया. देन अगर रेडियल सॉल्यूशन हम लेंगे, सब्स्टिट्यूटिंग द वैल्यू ऑफ बीटा इन द इक्वेशन, वी कैन हैव 1 by r square del by del r square del r by del r minus l into l plus 1 by r square more capital R plus twice mu by h cross square e minus u r is equal to 0. Or del square r by del r square plus 2 by r del r by del r plus minus l into l plus 1 by r square plus twice mu by h cross square e minus u r is equal to 0. This equation with u is equal to minus z square by r is called the radial equation for hydrogen-like atoms, and for z is equal to 1, it is radial equation for hydrogen atom. Now substitute u is equal to minus z square by r, and it is called radial equation for hydrogen-like atom, and for Z is equal to 1, it is a radial equation for your hydrogen atom. Z minus Z square by R होगा हाइड्रोजन लाइक एटम 1 इलेक्ट्रॉन सिस्टम. Z को अगर 1 पुट कर देंगे क्या होगा E स्क्वायर बाई R, ये होगा हाइड्रोजन एटम के लिए. Then del square R by del R square, del square capital R by del R square plus 2 by R del capital R by del R plus minus L into L plus 1 by R square plus twice M by H cross square E plus twice mu Z square by H cross R all multiplied by R, R is equal to capital R is equal to 0. According to classical mechanics, if E is smaller than 0, that is for negative energy, corresponds to elliptical orbits representing bound states in atomic system. While for E is greater than 0, that is positive energies corresponds to hyperbolic orbits representing the unbound states. But now in this case, let us consider that the electron is bound in the hydrogen atom. So we have to consider E is smaller than 0. So now substitute this and you can get alpha square is equal to minus 2 mu E by H cross square and your lambda is equal to mu Z0 square by H cross alpha. So your del square R by del R square plus 2 by R del R by del R plus minus L into L plus 1 by R square minus alpha square plus 2 mu by R multiplied by R is equal to 0. Now introduce the new independent variable rho such that rho is equal to 2 alpha R, where del rho by del R is equal to 2 alpha. So we have del R by del R, del capital R by del small r is equal to del R by del rho by del R is equal to 2 alpha del R by del rho, because capital R is a function of rho and rho is a function of small r. Now del square R by del R square is equal to del by del R, del of capital R by del of small r is equal to del by del rho 2 alpha del R by del rho multiplied by del rho by del R is equal to 4 alpha square del square R by del rho square. Now substituting these values of del R by del R and del square R by del R square in equation 4.45 and dividing by 4 alpha square. हाँ इंदिरानी जी बोलिए, आप रेज हैंड किए हैं?
है सर, यहाँ पर है.
ऐसे लग गया, ठीक है, ओके. So rho is equal to minus as rho is equal to 2 alpha r and del rho by del r is equal to 2 alpha. So you can see this chain rule and other things. Now you can see the asymptotic behavior of when a rho tends to infinite, the equation approaches of the form del square r, which is a function of rho by del rho square minus 1 by 4 r, which is a function of rho is equal to 0. The solution of the above equation is r, which is a function of rho, is equal to e to the power rho by 2, and r, which is a function of rho, is equal to e to the power minus rho by 2. As rho may vary from 0 to infinite, formula of this solution will increase as rho increases, and so it will lead to an unacceptable wave function. On the other hand, second solution decreases to 0 as rho increases to infinite. So the second solution is satisfactory. So you can have the recursion relation as I told you in your special functions. And after getting the recursion relation and see in the screen, these are the how recursion relation is being obtained. You can have the expression En is equal to minus mu z square e to the power 4 2h cross square n square. Okay, and this equation gives the energy eigenvalues for hydrogen atom with z is equal to 1 and is an agreement with the old quantum theory and experiment. Now the radial wave function can be discussed. Now substituting lambda is equal to n, we get rho g double dash lambda is equal to n in equation 4.57. We get rho g double dash plus 2 into L plus 1 minus rho g dash multiplied by g dash plus n minus L minus 1 multiplied by g is equal to 0. Now you substitute 2L plus 1 is equal to P and N plus 1 is equal to N dash. Now you can get rho G double dash plus rho plus P plus 1 minus rho G dash plus N dash plus P G is equal to 0. Now the solution of this equation will be the associated Laguerre polynomial, that is also a special function, or more correctly, the associated Laguerre polynomial multiplied by a constant factor, that is 0 is equal to C L subscript N dash superscript P rho is equal to C L subscript N plus L superscript 2L plus 1 rho, which is a function of rho, where C is a constant and may be made equal to the normalization factor. Now L subscript N plus L superscript 2L plus 1, which is a function of rho, is equal to summation K is equal to 0 to N minus L minus 1 minus 1 to the power K plus 1 N plus L factorial square rho to the power K by N minus L minus 1 minus K factorial 2L plus 1 plus K factorial K factorial. Thus the total wave function R, which is a function small r, is given by R NL, which is a function of R, is equal to e to the power minus rho by 2 rho to the power L G, which is a function of rho, is equal to C to the power minus rho by 2 rho to the power L subscript N plus L superscript 2L plus 1, which is a function of rho. The normalization condition for the physically significant interval of 0 to infinite is integration 0 to infinite capital R, which is a function of small r, r star is complex conjugate, which is a function of r square dr is equal to 0. Now the factor r square is necessary to convert the length dr into an element of a value. So you have rho is equal to 2 alpha r is equal to 2 multiplied by mu z square by s cross square lambda r, which is equal to 2 mu z square by s cross square n r, which is equal to 2r by n mu z square by h cross square is equal to 2z r by n multiplied by 1 by a0, where 1 by a0 is equal to mu e square by h cross square, where a0 being Bohr's radius. So now you can have r is equal to n a0 by 2z multiplied by rho. So you have dr is equal to n a0 by 2z multiplied by d rho. Now substituting values of r, which is a function of small r, and r star, so and also r and dr in equation 4.69, you can get c square integration 0 to infinite e to the power minus rho to the power 2l and your associated Laguerre polynomial square n a0 by 2z rho square n a0 by 2z d rho is equal to 1. Now solving this, you can have c is equal to root over of 2z by n a0 q multiplied by n minus l minus 1 factorial by 2n multiplied by n plus 1 l factorial 1 factorial to the power q. Now substituting these values of c in equation 4.68, the radial wave function may be represented as r subscript nl, which is a function of small r, is equal to root over of 2z by n a0 q n minus l minus 1 factorial by 2n multiplied by n plus l factorial q whole multiplied by e to the power minus zr by n a0 whole multiplied by 2zr by n a0 to the power l and your associated Laguerre polynomial, that is n subscript n plus l superscript 2l plus 1. Now you can have the first three radial function r10, r20 and r21. So r10 is equal to how much, which is a function of small r, z by a0 to the power 3 by 2 twice e to the power minus zr by a0. Similarly, the second radial function, that is r20, which is a function of small r, is equal to z by a0 to the power 3 by 2 multiplied by 2 into z minus r, z multiplied by r by a0 whole multiplied by e to the power minus z r a0. Similarly, the third radial function is r21, which is a function of small r, is equal to z by 2a0 to the power 3 by 2 multiplied by zr by a0 root over of 3 multiplied by e to the power minus zr by a0. Now the complete wave function is shown in the screen. The complete wave function of the normalized eigenfunction for hydrogen atom, hydrogen or hydrogen-like atom are psi nlm, which is a function of r theta and phi, is equal to rnl theta ml and phi m, with theta ml is equal to root over of 2l plus L multiplied by L minus modulus of M factorial by 2 into L plus M modulus of M factorial whole multiplied by P cos theta. P subscript L superscript modulus of M cos theta. Similarly, your phi m, which is a function of small phi, is equal to 1 by 2 pi e to the power I m phi, and your RNL, so which is a function of r, is equal to root over of 2z by n a0 to q multiplied by n minus l minus 1 divided by 2n multiplied by n minus l factorial q whole multiplied by e to the power zr divided by nh. The real forms of the complete eigenfunctions psi NLM exclusive of spin for various values of n, l and m are given below. n का वैल्यू अगर 1 होगा, l का वैल्यू 0 होगा, m का वैल्यू 0 होगा, ये 1s स्टेट आएगा. n का वैल्यू 2 होगा, l का वैल्यू 0 होगा, m का वैल्यू 0 होगा, 2s स्टेट आएगा. n का वैल्यू 2 होगा, l का वैल्यू 1 होगा, m का वैल्यू 0 होगा, 2p स्टेट आएगा. n का वैल्यू 2 होगा, l का वैल्यू 1 होगा, m का वैल्यू 1 होगा, that is also a 2p state. So eigenfunction for one state will be psi 111 can be written as 1 by root over pi z by a0 to the power 3 by 2 e to the power minus zr by a0. Similarly, 2a state are having eigenfunction psi 200 is equal to 1 by 4 root over pi z by a0 to the power 3 by 2 multiplied by 2 minus zr by a0 e to the power minus zr by a0. Similarly, 2p state का जो होगा आइजन फंक्शन psi 210 is equal to 1 by 4 root over pi multiplied by z by a0 to the power 5 by 2 multiplied e to the power minus zr by 2a0 r cos theta. Similarly, 2p state का होगा जहां आपका n is equal to 1, l is equal to 1 and m is equal to 1. Your psi
Hello. Is it over now, sir?